So far, we've been talking about probability distributions and characteristics for one event, but we also want to think about multiple events and their relationships with each other, especially when we're talking about pooling different events together. So, uncorrelated or independent events, I'm going to use these two terms synonymously in Methyl 131, even though technically speaking, they're not quite the same thing, but that's for Stat 230 to cover. But uncorrelated or independent events essentially means that the occurrence of one event doesn't tell us anything about the probability of the other event occurring. And so, for example, if somebody has a car accident in Waterloo, that doesn't tell us anything about the probability of a car accident in Paris. In France, for example, in a similar time frame. They're not related to each other. And so if, for example, probability of an accident in KW, let's say this is 0.005 versus probability of an accident in Paris, maybe 0.01. And so if these two events are independent, then the probability of both of them occurring, so accident in KW and in Paris in a similar time frame, is simply going to be the product of the probabilities of the individual events. And so we have 0.005 times 0.01, for example. So that's the independence case. And on the flip side, it could be that the events are correlated or dependent, where basically the occurrence of one event does tell us something about the probability of the other. It might be higher, right, because the first event occurred, or it might be lower because the first event occurred. And so, for example, or I guess maybe taking the same example, if we think about two different drivers in KW instead, in different parts of KW, right, what is it that might lead to accidents, right? We might have bad weather conditions, bad road conditions, for example. But the idea is that many of these things are going to be similar within the same area, right? And so then in that case, an accident in Waterloo by one driver versus an accident in Waterloo by a different driver, right? Those might be correlated, positively correlated events, right? They might move in a similar direction. And so in that case, if we consider the probability of two accidents in KW, in this case, if they are positively correlated, then the probability of two accidents in KW is not just going to be 0.005 times 0.005. It would actually be higher than that because the first accident occurring also makes it likelier that another accident is going to occur, right? They are correlated, they move in the same direction, right? How much do the observations move together? And so on the flip side, we can also think about negatively correlated events as well. Maybe a car accident here made it less likely for another car accident to occur in the same area. That is, this is probably not the best example for that, but you could potentially argue that could be the case. Maybe if a car accident happening made it so that everybody drove much safer, and then the second accident is less likely to occur, for example. But I think that's a bit of a stretch. Point being, losses, if they were correlated, do tend to be more positively correlated. And so to illustrate the idea behind pooling, right, how risk pooling works, let's basically consider first pooling uncorrelated or independent losses. And so let's start out with just a distribution for individual car accidents without pooling, right? Just considering an individual loss from an auto accident. And so in the simple distribution that we're given, we're basically saying that 5% of the time we have a $10,000 loss, and 95% of the time there's no loss at all, right? And so if we consider the expected loss per individual, right, this is an individual auto accident, then the expected loss is just each outcome weighted by the probabilities of that outcome, right? So we have $10,000 loss weighted by the probability 0.95 plus 0 as the other outcome weighted by 0. Flipped the probabilities. 0.05, 0.95, right? And so the overall expected loss in this case would be $500. And so the standard deviation for this individual loss, right, without any pooling so far, just looking at this individual loss, once again, this is going to be the average, right, the squared difference of each outcome from the mean weighted by the probabilities. And so the first one, right, 10,000, subtract the mean is 500, squared weighted by the probability of that outcome, plus the second outcome, 0, minus the mean, squared weighted by the probability of that outcome, which is, in this case, 4,750,000, right? Maybe I should add that this is the variance. And so that means that the standard deviation is just the square root of the variance, which in this case is around $2,179.45, right? So we have our expected loss per individual loss and our standard deviation per individual loss. And so this is all without pooling so far. And so now we want to think about, what happens when two people pool each other's losses, and here they're also sharing. Okay, and so I want to clarify that pooling and sharing are not synonymous. And so what does pooling mean? Pooling basically means that we're drawing together many observations to be able to better predict, right? To be able to more accurately estimate a loss for prediction purposes. Whereas sharing means that we are also deciding to pay for each other's losses as well, also equally share in paying out the losses. And so, for example, then sharing always involves pooling, but not vice versa, right? So you may pool observations together just to better predict, but sharing means that you are, in addition to pooling losses together, you are also sort of deciding to share in the payment of each other's losses, right? So in this case, we have pooling and sharing, but just recognizing that, we don't necessarily always have sharing. But in this case, we're pooling and sharing losses. And so here we have two people. They decide that if someone has a loss, that they'll equally split the losses, right? So that's pooling and sharing. And we want to create a new probability loss distribution for each individual person when they are doing this pooling and sharing. And so we want to create a loss distribution for the two people's losses. And so we want to think about all of the possible outcomes between these two people and assign probabilities to each of those outcomes, right? So when we have two people this time, then one possible outcome is that both of them suffer losses, right? Both of them have a car accident. And so if that were the case, then the total outcome itself would be, their total losses would be 10,000 plus 10,000, right? So 20,000. And so that means they would each be paying 10,000 because they're equally sharing in the losses. And what's the probability of this happening? Assuming independence, right? Assuming independence, then we're just going to take the probability of the individual losses, right? So this would be 0.05 times 0.05, which is 0.0025, right? So we have one outcome is if both of them experience a loss. We can also have just one of them experience a loss. And so if that were to happen, then the total losses for both of them put together is 10,000 because only one of them experienced a loss, right? For each individual person, then that means they are splitting this loss, right? With the sharing, that means that they would be paying $5,000. And what's the probability of that occurring, right? That would be if the first person has a car accident and the second person does not have a car accident. But it could also be that, the first person does not have a car accident and it's the second one that has a car accident, right? Recognizing that there are two ways of having $10,000 as the total loss between the two. And so this is going to be equal to 0.095. And then lastly, it could be the case that, most likely actually, both of them do not have a car accident. And so the total outcome would be 0. And so each individual outcome would also be 0. And so the probability of that occurring, again, assuming independent events, would be 0.95 times 0.95, which is going to be 0.9025. Right? And so we've now created a probability distribution of all of the potential outcomes when there are two people involved, right, who are pooling and sharing losses. And so this is basically our probability distribution for each individual person under all of these situations, whether one of them has an accident, whether both of them have an accident, whether, maybe both of them don't have an accident either. And so the payments that each individual person would have to make and the probabilities associated with each one. So as a quick sort of sanity check, we can verify here that the probabilities across all of the outcomes does sum to 1, right? So they are collectively exhaustive and also mutually exclusive, right? If a loss is equal to $10,000, then it can't also be equal to $5,000, for example. So now, just like the individual case, we want to consider what happens for an individual that happens to be in this two-person pooling and sharing arrangement, right? What is the expected loss per individual, and what is the standard deviation of the loss for each individual when they are pooling and sharing their losses in this case? And so pulling up the probability distribution that we just derived, right, the expected loss per person once again, each outcome weighted by the probability, sum over all possible outcomes. So we have 10,000, 0.0025, 5,000, 0.095 plus 0 with probability 0.9025. And so the expected loss per individual is still going to be 500. Right? This is actually the same as the individual's expected loss without pooling, right? But let's then consider this standard deviation of the loss per individual. And so we're going to calculate the variance first. So the variance of the loss per person, right, of this derived distribution that we've derived, I guess. So for each outcome, right, subtract the mean squared weighted by the probability of that outcome. So 10,000 subtract 500 squared weighted by 0.0025 plus 5,000 subtract the mean squared weighted by 0.095, and then lastly 0 minus the mean 500 squared weighted by its probability 9025, right? And so this is going to be 2,375,000, and so that means the standard deviation per person with the pooling and sharing is going to be the square root of this is going to be 1,541. And so it's actually gone down compared to the individual case. I think before it was something like 2,000 something. And so the idea here is that when we're combining individual, right, when we're combining independent individual units, the standard deviation per individual decreases, but the expected loss remains the same. And so when you're pooling independent losses, the risk per person decreases, right? The relative risk decreases. And so that was just two individuals, right? So it's very easy to list out all of the possible outcomes and derive all of the probabilities associated with them. But we can also consider, right, building on top of that, the general case of more and more people, right, pooling more and more independent losses joining the pool, and then think more about the general case. And so here I'm going to rely on simulation to build the distribution for an individual's pooled and shared losses as the size of the pool grows, right? Because we can't really, it's not going to be so straightforward to derive by hand. And so here are the distributions for each individual's pooled and shared losses with more and more independent individuals as they join the pool from left to right. And so, for example, we can consider pooling 50 individuals or 100 individuals or 1,000 individuals. What does the distribution of one individual's losses look like with the pooling and sharing? Right? And so these three graphs, they all have the exact same x-axis, so we can easily compare the distributions. And so we can see that the expected loss per individual, which is the blue dotted line, the vertical blue dotted line, is the same, is at that 500, regardless of how many people are in the pool, right? So the expected loss per person is the same, but it's the dispersion around the mean, right, that's decreasing as the size of the pool grows, right? The relative dispersion is decreasing as the size of the pool grows. And this is, again, for pooling in independent losses. We can also see, actually, here that the pooled and shared losses for an individual, the distributions are becoming more and more normally distributed as well. And again, there's going to be more of this in Stat 230. I don't expect you to know what a normal distribution is, right, by definition, but you can basically think of it as your sort of standard sort of symmetric bell curve, right? And so the important sort of observation here is basically the relative risk, or the risk per individual, is decreasing as we pool together more and more independent individuals. And so to formalize this a little bit, again, you'll get a far more mathematically precise definition in Stat 230. This is known as the law of large numbers. Essentially, as the number of observations increases, the relative dispersion decreases. And so our numerical example, right, with the two-person pooling and sharing was for independent losses, and so were all of these previous simulated distributions. But again, we want to consider the effects of positive and negative correlation because oftentimes in the real world, right, it is possible that different kinds of events are related to each other. For example, two people in the same city or the same apartment would face very similar road or weather conditions, would face very similar potential losses due to, climate-related catastrophes. And so if one person has an accident, it's possible, it's more likely that another person will have an accident as well. When positive correlation exists, right, random variables kind of moving in similar directions, it basically reduces the effect of pooling. It doesn't necessarily eliminate the effect unless these are perfectly positively correlated events where, every single time one loss happens, the other loss happens as well, right? If that's the case, then there's no benefit to pooling. But in general, when there is, when it's not perfectly positively correlated, but there is positive correlation, then it reduces the benefit, it reduces the effect of pooling. Because if we think about it sort of intuitively, what's going on in the distribution of the total losses, then there's going to be more probability mass at both extremes, both sets of extremes, right? The probability of both car accidents occurring becomes larger, and also the probability of both car accidents not occurring also increases. And so the expected loss still stays the same, but there's just, greater dispersion compared to if the losses were independent. So there is still benefit to pooling, as in it's still better to pool than to not pool, but it's just that benefit decreases in the presence of positive correlation. Right? And so it's more difficult to achieve pooling, more effective pooling, when situations are positively correlated. And so from a more sort of risk management perspective, right, we want to be able to work toward achieving independence, relative independence, and find opportunities to pool relatively independent events to manage the risk. And so if we look at the diagram here, this is once again simulated losses. This is basically comparing the distribution for each individual with pooled and shared losses across 100 or 1,000 independent losses. Previously, we've seen the independence case in the red or the pink, right, compared to
if these were to be positively correlated losses, that's the distribution in the blue here. If we're pooling together 1,000 positively correlated losses, that's what the distribution looks like for one individual's pooled and shared losses. And so there's, again, sort of greater probability in both ends of the distributions, so that the expected value is still the same, but there is now higher relative dispersion compared to the independent case. Again, so there is still some benefit to pooling. It's just a reduced benefit compared to the independent case. And so it's still better than no pooling, right? Still better than the individual's losses, which were, remember, what were they? It was either 0 or it was 10,000, right? There's a lot of variability there. And so on the flip side then, right, negatively correlated events would actually improve the benefit of pooling. It's just that oftentimes, or pooling compared to the independent case, it's just that oftentimes we don't actually observe negative correlation in the realm of pure risks, right? Because in the realm of losses, all the outcomes are either 0 or negative. And so actually having them move in opposite directions doesn't really exist when our outcomes are all, negative. And so I think that organizationally, there is potential to find negative correlation if you're analyzing pure and speculative risks together. But again, when we're talking just about, the realm of losses, just pure risks, typically we don't tend to observe negative correlation. And so it is, losses do tend to be positively correlated if correlated. And so that's why we spent more time sort of comparing the positive correlation case compared to the independence case. And so, right, pooling is one risk management tool that can help reduce risk. And so identifying opportunities to pool within an organization, right, that might involve internal risk reduction. For example, like I mentioned earlier, pooling doesn't necessarily always include sharing. Pooling is just simply having a large number of observations to be able to better predict, right? So for example, Amazon observing their own self-driving car accidents, right? That allows them to better predict future car accidents, reduce the risk in some sense from the pooling, from the more accurately being able to predict. Considering, full sort of enterprise risk management, also the opportunity basically to combine risks across an entire organization, which can then allow us to maybe combine some speculative with pure risks and obtain those kinds of negative correlations potentially. As far as pooling opportunities go, we can also think about compensation in liability, right? Oftentimes, actually, the courts might hold a party liable if they are the ones that are, can better pool the observations than the individuals being affected, right? For example, that's one reason why strict liability is allowed, right? The feeling is that the manufacturer should have been able to better pool all of the observations of the people buying the product and the accidents that might occur and better predict, better anticipate what will happen than any individual person just buying the product,